In the silent, unending theatre of the cosmos, there are monsters. They are not creatures of flesh or fury, but of gravity itself. They are voids, absences, points of such profound impossibility that they tear the very fabric of existence asunder. We call them black holes. From our distant, safe perspective, we see their effects. We watch as they command the orbits of entire galaxies. We witness stars, incandescent giants of gas and fire, drawn into an inexorable, spiraling dance of death, shredded into ribbons of superheated plasma before they vanish. The darkness consumes them, and in return offers only silence. For centuries, we have studied them from afar, charting their shadows, measuring their immense gravitational influence. We have learned how they are born in the cataclysmic death of stars, and how they grow by devouring everything that strays too close. We have mapped the boundary of no return, the event horizon, the final precipice at the edge of known reality. But this is all a study of the outside, of the cage. It tells us nothing of the beast that dwells within. What happens when you cross that threshold? What secrets, what truths, what form of reality or unreality is concealed behind that perfect curtain of blackness? This is perhaps the greatest mystery in all of science, a question that pushes our understanding to its absolute limit and beyond. What truly lies hidden inside a black hole? The journey to an answer begins not in the depths of space, but in the depths of the human mind, over 2 centuries ago. In 1783, a quiet English philosopher and clergyman named John Michel, gazing at the same night sky we see today, posed a revolutionary, almost heretical question. He reasoned that light, though seemingly weightless, was a particle, and if it was a particle, it must be affected by gravity. Therefore, a star sufficiently massive and compact could possess a gravitational pull so immense that even light could not escape. He called these theoretical objects dark stars. It was a staggering leap of intuition, an idea so far ahead of its time that it was largely forgotten, a footnote in the history of astronomy. Physics simply had no language to describe such an object. That language would not arrive for another 130 years, and it would be delivered by a mind that would forever change our perception of space, time, and gravity. Albert Einstein, with his theory of general relativity published in 1915, did not set out to find monsters in the cosmos. He sought to understand the fundamental nature of gravity. His revolutionary insight was that gravity was not a force, but a curvature, a warping of a 4-dimensional fabric called space-time, caused by the presence of mass and energy. Imagine a stretched rubber sheet. A bowling ball placed in the center will create a deep depression, a curve. A marble rolled nearby will not be pulled by the ball, but will instead follow the curve created by its presence. This, Einstein proposed, is how gravity works. Planets orbit the sun because they are following the immense curve in space-time that the sun's mass creates. His equations were elegant, beautiful, but notoriously difficult to solve. Einstein himself could only find approximate solutions. The first person to find an exact solution was a German physicist and astronomer named Karl Schwarzschild, and the circumstances of his discovery are the stuff of legend. He achieved this monumental feat not in a comfortable university office, but in the frozen, muddy trenches of the Russian front during World War I, calculating complex tensor equations by candlelight amidst the chaos of battle. Schwarzschild's solution described the gravitational field outside a single, non-rotating spherical mass. But buried deep within his mathematics was something deeply strange. It predicted that if you could compress that mass into a small enough sphere, a volume now known as the Schwarzschild radius, the curvature of space-time would become infinite. It would, in essence, punch a hole in reality itself. At the center of this hole would be a point of zero volume and infinite density, a place where all the mass had collapsed. He had mathematically described a black hole. Einstein was horrified. He thought the idea was a mathematical quirk, a monstrosity that nature would surely forbid from ever forming. He believed some unknown physical principle would prevent such a total collapse. For decades, this remained the prevailing view. But the universe, it turned out, was far more violent and far more creative than even Einstein could imagine. We now understand that the crucibles for these objects are the hearts of the most massive stars in the cosmos. For millions of years, these colossal stars burn, fusing lighter elements into heavier ones in their cores. This process, nuclear fusion, creates a tremendous outward pressure. This pressure is in a constant, delicate battle with the star's own immense gravity, which is relentlessly trying to crush it inward. It is a stalemate that defines the star's entire life. But this cosmic balancing act cannot last forever. Eventually, the star exhausts its nuclear fuel. With the outward pushing furnace extinguished, gravity wins. And it wins instantly and catastrophically. The star's core collapses in on itself in a fraction of a second. The outer layers, suddenly unsupported, come crashing down, rebounding off the impossibly dense core in a titanic explosion we call a supernova. For a few brilliant weeks, this single dying star can outshine its entire galaxy, blasting heavy elements across the cosmos, the very elements that will one day form new stars, new planets, and new life. But for the most massive of stars, something far stranger is left behind. If the remnant core is more than about 3 times the mass of our Sun, no known force in the universe can halt its continued collapse. Not the pressure of electrons, not the pressure of neutrons, nothing. Gravity, unopposed and absolute, crushes the core down, past the point of a neutron star, down past any conceivable limit, squeezing all of that mass into an infinitely small point. The singularity is born. And around it, the event horizon springs into existence, a one-way membrane separating this new, bizarre region of space-time from the rest of the universe. Einstein's mathematical monster was real. To truly understand the strangeness of this boundary, let us imagine a journey. Let us send a brave hypothetical astronaut, we'll call her Elara, on a mission to investigate a stellar mass black hole. From a safe distance, her view is distorted, as if looking through a warped lens. The black hole's gravity bends the light from the stars behind it, a phenomenon known as gravitational lensing. The black hole itself is just a perfect circle of blackness. Against the backdrop of the star field, an absolute void. As Elara fires her thrusters and begins her descent, 2 profound things start to happen, dictated by Einstein's relativity. The first is a brutal physical process. The gravitational pull of the black hole is so extreme that the force on her feet is exponentially stronger than the force on her head. This tidal force begins to stretch her, and her ship, pulling them apart like dough. This process, with a chillingly literal name, is called Spaghettification. Long before she reaches the boundary, her body and her vessel would be torn into a stream of individual atoms, a thin ribbon of matter spiraling down into the abyss. But let us grant Elara a magical, indestructible ship so we can explore the second, more mind-bending effect, time dilation. To an observer, her friend Kai, watching from a safe distance, Elara's journey seems to slow down. As she gets deeper into the black hole's gravitational well, her clocks tick slower relative to Kai's. Her signals take longer and longer to reach him. The light from her ship becomes redder and dimmer, its wavelength stretched by the extreme gravity. As she approaches the event horizon, Kai would see her image, slow to a near-complete stop, frozen in time, fading over an eternity until she is no longer visible. From his perspective, she never, ever crosses the boundary. But from Elara's perspective, nothing seems unusual about her own time. Her clocks tick normally. She feels no sense of slowing down. For her, the journey to the event horizon takes a finite amount of time. Looking back, she would see the entire future history of the external universe play out in fast forward, like a frantic film. Stars are born and die, galaxies collide, the cosmos ages in an instant. and then she crosses it. The event horizon is not a wall, it is not a surface, it is not something you would feel or collide with. It is simply a location in space-time. It is the point where the curvature of space-time becomes so extreme that the escape velocity exceeds the speed of light. It is the ultimate point of no return. Imagine a wide, slow-moving river. Boats can sail on it freely, even against the current, but as the river narrows, its speed increases. Eventually, it reaches the edge of a colossal waterfall. There is a line in the water before the falls where the current becomes faster than any boat's maximum speed. Once a boat crosses that line, no amount of engine power can save it. Its fate is sealed. It is destined to go over the edge. The event horizon is that line in the river of space-time. The moment Alara crosses that threshold, her reality is fundamentally transformed. Outside the black hole, you are free to move in any direction in space, but you are inexorably forced to move forward in time. Inside the event horizon, these roles are swapped. Space itself is flowing inward, faster than light, carrying everything with it towards the center. Now, she has no choice but to move inward through space. The direction toward the singularity becomes her future. She can no more avoid hitting the singularity than we, on the outside, can avoid next Tuesday. It is no longer a place in space. It is a moment in time. It is her appointment with destiny. So, what does she see? The physics we know, the physics of general relativity, gives us a chilling and ultimately incomplete answer. It tells us that Alara and the stream of atoms she has become will continue their journey inward, crushed by ever-increasing tidal forces until they reach the center. There, at the heart of the black hole, lies the singularity. The classical singularity is a concept that breaks physics. It is a point of zero volume, yet it contains all the mass of the collapsed star. This means its density is infinite. The curvature of space-time there is also infinite. At this point, all the known laws of physics, all the equations of general relativity, break down. They produce answers of infinity, which is mathematics, a way of screaming that it no longer understands what is happening. It is the end of space and the end of time. It is, for all intents and purposes, a physical nothingness that contains an impossible everything. For many decades, this was the end of the story. A point of infinite destruction from which nothing, not even information, could escape. But this picture is profoundly unsatisfying to a physicist. Nature abhors infinities. They are almost always a sign that a theory is incomplete, a placeholder for a deeper truth we have yet to uncover. General relativity is a magnificent theory of the very large, of stars, galaxies, and the cosmos. But the singularity is a problem of the very small. And to understand the very small, we need a different set of rules. We need the strange, probabilistic, and mind-altering laws of quantum mechanics. The conflict between these two great pillars of modern physics, general relativity and quantum mechanics, is the central challenge of our time, and the interior of a black hole is their ultimate battleground. It is the one place in the cosmos where both theories must apply, and where they spectacularly fail to agree. The key to understanding what truly lies inside a black hole is the key to uniting them, to finding a theory of everything. One of the first and most profound insights into this conflict came from the brilliant mind of Stephen Hawking in the 1970s. Hawking decided to apply the principles of quantum mechanics to the region just outside the event horizon. According to quantum field theory, empty space is not empty at all. It is a roiling, bubbling soup of virtual particles which pop into existence as matter-antimatter pairs, exist for a fleeting moment, and then annihilate each other. This is the quantum foam, the fundamental graininess of reality. Hawking realized that if a pair of these virtual particles were to pop into existence right at the edge of the event horizon, it was possible for one particle to fall into the black hole while the other escaped into space. Because the particle that fell in could no longer annihilate its partner, the escaping particle becomes real. To a distant observer, it would look as though the black hole itself was emitting a faint glow of radiation. This phenomenon became known as Hawking radiation. The implications of this are staggering. The escaping particle carries away energy, and since mass and energy are equivalent according to E equals mc squared, the particle carries away mass. This means that black holes are not truly black, and they are not eternal. They evaporate. The process is excruciatingly slow. For a black hole the mass of our Sun, it would take 10 to the power of 67 years to evaporate completely, an amount of time so vast that the current age of the universe is an insignificant rounding error by comparison. But it means that eventually, every black hole in the universe will radiate itself away until nothing is left. This raised an even deeper paradox, one that still confounds physicists today, the black hole information paradox. A fundamental principle of quantum mechanics is that information cannot be destroyed. The information about a particle, its position, its velocity, its quantum state, can be scrambled, but it must, in principle, always be recoverable. If you burn a book, you could theoretically reconstruct the text from the positions of every atom of ash, smoke, and heat. But what happens to the information of all the matter that falls into a black hole? When Alara crossed the event horizon, all the unique information that made her times went with her. If the black hole completely evaporates into a featureless thermal glow of Hawking radiation, where does that information go? Is it truly destroyed, violating one of the core tenets of physics? Or is it preserved in some way we don't yet understand? Solving this paradox forces us to reconsider the classical picture of the singularity. It suggests that something else must be happening at the center, something that both prevents the formation of an infinite point and provides a mechanism for storing and eventually releasing information. Here, we leave the shores of established physics and venture into the speculative oceans of modern theoretical research. There are several leading and wildly different ideas about what might replace the singularity. One compelling idea comes from a theory called loop quantum gravity. This theory attempts to quantize space-time itself, suggesting that space is not a smooth, continuous sheet, but is made of discrete, indivisible atoms of space-time, like pixels on a screen, at the incredibly tiny Planck scale. According to this theory, as matter collapses to form a black hole, it can't be crushed to an infinitely small point because there is a minimum possible size. Instead, the inward crush of gravity becomes so immense that it triggers a powerful outward-pushing quantum force, a kind of space-time repulsion. The collapse is halted, and the matter rebounds, forming an unbelievably dense but finite object called a Planck star. From the outside, this object would be indistinguishable from a classical black hole. It would have the same mass and the same event horizon, but inside there would be no singularity. Instead, there would be this quantum object, a compressed spring of space-time containing all the matter and information that ever fell in. For an incredibly long time, the Planck star would sit there as the black hole slowly evaporates via Hawking radiation. As the black hole shrinks, the Planck star at its core remains the same size. Eventually, the shrinking event horizon would reach the Planck star. At this point, the spring would be released. The Planck star would explode, releasing all of its stored information back into the universe. In this view, a black hole is not a permanent prison, but a temporary one, a place of cosmic hibernation. A very different and equally compelling picture emerges from string theory, the other leading candidate for a theory of everything. In string theory, the fundamental constituents of reality are not point-like particles, but unimaginably small, one-dimensional, vibrating strings. Different vibrations of these strings give rise to all the different particles and forces we see in the universe, like different notes played on a violin string. From this perspective, a black hole might not be a singularity at all. Instead, it could be a giant, tangled, messy ball of these fundamental strings, what theorists call a fuzzball. In the fuzzball model, all the matter that falls into the black hole is converted into a complex configuration of strings. This fuzzball has a real, physical surface, but it exists where the event horizon was thought to be, there is no empty space inside, no journey to a central point of doom. The entire volume is filled with this exotic state of stringy matter. This idea elegantly solves the information paradox. The information of everything that falls in is not lost. It is woven into the complex vibrational patterns of the fuzzball's surface. As the black hole radiates, this information is slowly and subtly encoded in the outgoing Hawking radiation, like a cosmic hologram. The event horizon, in this picture, is not a sharp boundary, but a blurry, quantum, information-rich surface. And then there are the even more speculative, more mind-bending possibilities. When Schwarzschild first solved Einstein's equations, his mathematics didn't just describe a black hole. The full solution also mathematically described its opposite, a white hole, a region of space-time from which matter can only escape but never enter. This led to the concept of an Einstein-Rosen bridge, more famously known as a wormhole. This is the idea that a black hole could act as an entrance and a white hole as an exit, connecting two distant points in space-time, or perhaps even connecting to another universe entirely. For Alara, this would mean that after crossing the event horizon, she wouldn't be crushed at a singularity. Instead, she would travel through a short throat and be violently expelled from a white hole somewhere else. While this remains a valid mathematical solution, most physicists believe that such wormholes would be incredibly unstable. The slightest perturbation, even a single photon, would cause the throat to collapse instantly, turning the bridge back into a deadly singularity. It's a tantalizing possibility, a staple of science fiction, but one that nature may have ultimately forbidden. Yet, this idea of other universes connects to one of the most profound and philosophically resonant theories about the interior of black holes. Proposed by physicist Lee Smolin, the theory of cosmological natural selection suggests that the singularity at the heart of a black hole could be the seed for the birth of a new universe. The conditions inside a black hole, unimaginable density and energy, are remarkably similar to the conditions of our own Big Bang. Perhaps when matter collapses to a singularity, it doesn't just end, it rebounds and triggers a new Big Bang, creating a baby universe with its own space and time, forever causally disconnected from our own. If this is true, our own universe may have been born from a black hole in a parent universe. And every black hole in our cosmos could be a cosmic womb, giving birth to countless child universes. This theory even provides a mechanism for cosmic evolution. Universes that have physical laws that favor the creation of black holes will have more offspring. Our universe, which is clearly very good at making black holes, might be the result of eons of this cosmic survival of the fittest. In this breathtaking vision, the singularity is not an end, but a beginning. It is the engine of cosmic fertility, a gateway to eternal creation. So, where does this leave us? What is truly inside a black hole? Is it the infinite oblivion of a classical singularity, a hyperdense quantum star waiting to rebound, a tangled, holographic fuzzball of cosmic strings, a gateway to another place, another time, another universe? Or is it something so utterly alien that we have not even begun to develop the concepts needed to describe it? The truth is, we do not know. And we may never know for sure. The event horizon stands as the ultimate barrier, a cosmic sensor that shields the interior from our direct observation. No information can escape from within to tell us the answer. Any probe we send, any brave astronaut like Alara, is lost to us forever the moment they cross that threshold. But this does not mean the question is unanswerable. The answer lies hidden in the mathematics of a unified theory of physics. It is encoded in the grand equation that will finally weave together the elegant curves of space-time with the fuzzy uncertainty of the quantum world. When we find that theory, we will be able to describe the interior of a black hole with the same confidence that we now describe the orbit of a planet or the structure of an atom. Until then, the black hole remains the ultimate cosmic enigma. It is a physical object, yes, a gravitational leviathan roaming the celestial ocean. But it is also something more. It is a symbol of the limits of our knowledge. It is a crucible where our most successful theories are burned away, forcing us to search for something deeper, something more true. It represents the profound, humbling, and thrilling realization that the universe is not only stranger than we imagine, it is stranger than we times can times imagine. The silent, perfect blackness that hangs in the void is not an absence. It is a question. And in our relentless pursuit of an answer, we are forced to stretch our minds, to dream bigger, and to push forward into the unknown. For locked inside that darkness may lie the ultimate secret of existence itself. How can something be and not be at the same time? It is a question that seems to violate the very foundation of logic, a paradox that our minds are built to reject. Yet, for nearly a century, one of the most enduring images in all of science has forced us to confront this very impossibility. You know the image. Even if you've never opened a physics textbook, you have felt its presence. It lurks in the cultural shadows, a ghost of an idea, a whispered riddle. It is the spectre of a cat sealed away in a cold steel box, its fate hanging on the most delicate of threads. Inside this cruel hypothetical prison, a single radioactive atom holds the power of life and death. If it decays, an event governed by the bizarre probabilistic laws of the quantum world, it triggers a hammer. The hammer shatters a vial of hydrocyanic acid, and the cat dies. If the atom does not decay, the cat lives. From our perspective, outside the box, we cannot know. And so, we are told, the universe itself remains undecided. The atom is not decayed or undecayed. It exists in a ghostly blend of both states, a superposition. And because the cat's fate is chained directly to that atom, it too must inherit this quantum weirdness. It is not alive or dead. It is somehow suspended in an unimaginable state of being both. A phantom heartbeat and a final stillness, coexisting in the dark, a living creature and a corpse, occupying the exact same space at the exact same time. Only when we open the box, when our consciousness intrudes upon this delicate system, does the universe finally make up its mind. The wave of possibility collapses into a single concrete reality. We look, and in that moment of observation the cat becomes one or the other. It is either purring, or it is gone. This is Schrödinger's cat. It has become the ultimate symbol of quantum mechanics, a shorthand for the bewildering nature of reality at its most fundamental level. It's a concept so strange, so counterintuitive, that it has broken free from the confines of the laboratory and lecture hall. It has become a meme, a plot device in science fiction, a philosophical touchstone for late-night debates about the nature of existence. It whispers to us a tantalizing and terrifying possibility, that reality itself is not solid and fixed, but is instead a shimmering probabilistic fog until the act of looking at it forces it to take a definite shape. It suggests we are not passive observers of the cosmos, but active participants in its creation, our gaze turning ghostly potential into concrete fact. This interpretation has captivated us because it speaks to a deep human intuition that the world is more mysterious than it appears. It validates the feeling that beneath the surface of our mundane classical world of solid objects and predictable outcomes, there lies a hidden realm of magic and uncertainty, a world where a cat can, for a fleeting moment, straddle the abyss between life and death. This is the story you have been told, the story we have all been told, and it is almost entirely wrong. What if we told you that the very man whose name is forever attached to this paradox, Erwin Schrödinger, did not believe it for a second? What if this famous thought experiment was not a sincere attempt to describe the world, but a brilliant, biting piece of sarcasm, a cry of intellectual protest, designed not to illustrate the truth of quantum mechanics, but to expose its utter absurdity when taken to its logical conclusion? The story of Schrödinger's cat is not the story of a half-dead, half-alive animal. It is the story of a rebellion. It is the tale of a titan of physics, a Nobel laureate who helped build the quantum revolution, looking upon his own creation with a growing sense of horror. Schrödinger wasn't trying to tell us that the world is this strange. He was screaming, with all the intellectual force he could muster, that it couldn't possibly be. To understand this, we must journey back to one of the most volatile and exciting periods in the history of human thought. The early 20th century, when the neat clockwork universe of Isaac Newton was being shattered. A new generation of physicists wrestling with the bizarre behaviour of a light and matter at the atomic scale were forging a new set of rules that were stunningly successful at predicting the results of experiments, yet described a reality that seemed to defy all common sense. At the heart of this new physics was the Copenhagen interpretation, championed by the formidable figures of Niels Bohr and Werner Heisenberg. They proposed a world of innate uncertainty, of particles that are waves, of properties that do not exist until they are measured. To them, the subatomic world was a realm of pure potential. An electron wasn't in any one place. It was a cloud of probability, a wave function describing all the places it could be. Only a measurement, an observation, could force this ghostly cloud to condense into a single point. For Bohr and Heisenberg, this wasn't an admission of ignorance. It wasn't that we just didn't know where the electron was. They were making a far more radical claim, that before the measurement, the electron truly wasn't anywhere in particular. Its position was fundamentally, ontologically undefined. This was the idea that Schrödinger, along with his friend and intellectual ally Albert Einstein, found so deeply repugnant. Einstein famously railed against it, declaring that God does not play dice with the universe. He believed there must be a deeper, more orderly reality hidden beneath the veil of quantum probabilities. Schrödinger shared this profound unease. He saw the Copenhagen interpretation as a surrender, an abandonment of the physicist's duty to describe what whiz. He was an architect of the new quantum theory. His own Schrödinger equation is a cornerstone of the field, describing precisely how those waves of probability evolve over time. Yet, he could not accept the philosophical leap his colleagues were making. To him, it was one thing to speak of a single, invisible electron existing in a fuzzy state of superposition. Our intuition fails us at that scale, but reality is seamless. The laws that govern the atom must eventually connect to the laws that govern the objects we see and touch every day. There cannot be two different sets of rules for the universe, one for the small and one for the large. There must be a bridge. And it was on this bridge that Schrödinger decided to stage his protest. He would take the abstract, almost mystical idea of superposition and drag it, kicking and screaming, out of the ghostly atomic realm and into our familiar macroscopic world. He would force his colleagues to confront the monstrous implications of their own theory. In a series of letters and a famous 1935 paper, he devised his diabolical thought experiment. He wasn't proposing a real experiment, but a conceptual weapon. The cat was his hostage. He chose a living creature deliberately for maximum rhetorical and emotional impact. You cannot so easily dismiss the state of a cat as being undefined. Life and death are the most definite states we know. The entire apparatus, the box, the atom, the hammer, the poison, was a meticulously engineered device for magnifying quantum weirdness. It was a diabolical contrivance, in his own words, designed to create an unbreakable link between the microscopic and the macroscopic. The fate of the atom, which the Copenhagen school insisted was in a superposition of decayed and not decayed, was now inextricably chained to the fate of the cat. If the atom's state is truly a blend of two possibilities, then the cat's state must be a blend too. The CI function of the entire system, he wrote with barely concealed scorn, would express this by having in it the living and dead cat mixed or smeared out in equal parts. This was his masterstroke, his checkmate. He was holding up a mirror to his colleagues and saying, yes, look at the reflection of your theory. It leads to this, a living dead cat, an absurdity, a contradiction of everything we know about reality. Are you truly prepared to accept this? He was certain they would be forced to recoil, to admit that their interpretation must be incomplete, that something was missing from the story. He believed he had exposed a fatal flaw in the Copenhagen interpretation, the point where its logic, when extended beyond the subatomic domain, shattered against the bedrock of observable reality. But history took a strange and ironic turn. Instead of killing the interpretation, Schrödinger's thought experiment became its most famous, albeit misunderstood, illustration. The world, fascinated by the bizarre image he had concocted, largely missed the sarcasm. They forgot that it was intended as a parody, a warning. The cat escaped its creator's intellectual leash and came to symbolize the very mystery he was trying to dismantle. And in doing so, it left us with the most profound question in all of modern physics, a question Schrödinger was the first to so vividly articulate. Where does the quantum world end and our world begin? This is the so-called measurement problem. If an atom can be in two states at once, why can't a cat, or a planet, or you? At what point, and through what mechanism does the universe force a choice? What constitutes a measurement? Is it the click of a Geiger counter? Does it require a conscious observer, a human mind to perceive the outcome? Or does the interaction of a quantum system with its vast, complex environment, a process called decoherence, effectively make the choice for us, collapsing the superposition so quickly that we never see a smeared-out cat? The puzzle of Schrödinger's cat is not about feline biology. It is about the chasm that separates the two great pillars of physics: quantum mechanics, the theory of the very small, and general relativity, the theory of the very large. It is the central mystery that physicists have been battling for a century, giving rise to ever more exotic theories in an attempt to solve it. Theories of parallel universes, where the cat is alive in one world and dead in another. Theories of hidden variables, just as Einstein suspected, that would restore a clockwork order to the quantum chaos. Theories that rewrite the rules of logic itself. In this series, we will pull back the curtain on this epic scientific and philosophical drama. We will strip away the layers of myth and misinterpretation to reveal the true story of Schrödinger's cat. We will journey into the heart of the quantum realm, a place more alien than you can possibly imagine. We will meet the brilliant, passionate, and often combative minds, Bohr, Heisenberg, Einstein, and Schrödinger himself, who waged a war over the very soul of reality, and we will explore the cutting-edge experiments of today, where scientists are pushing the boundaries, creating their own Schrödinger's kittens in the lab. Not with living creatures, but with microscopic objects placed into states of quantum limbo, all in a relentless quest to find the seam that stitches our comfortable classical world to the bizarre quantum foundation upon which it rests. This is not just a story about physics, it's a story about how we know what is real. It's about the profound and unsettling realization that the world we perceive with our senses is merely the surface of a much deeper, stranger, and more mysterious ocean of existence. The box is closed, the thought experiment has begun, and our journey is to understand what truly happens inside in the dark when nobody is looking. Nobody is... What if reality, the solid, dependable reality you experience every moment, is just a facade? What if, beneath the world of concrete certainty we all inhabit, there exists a realm of pure, shimmering potential? A world where things are not one way or another, but all ways at once. This wasn't a question posed by mystics or philosophers in ancient temples. It was the terrifying, exhilarating conclusion being reached by the brightest minds in physics, in the heart of a Europe still reeling from one great war and hurtling unknowingly toward another. To understand the infamous cat, we must first journey back to that time, to the roaring 1920s and the turbulent 1930s. It was an age of explosive creativity, of jazz and Art Deco, but also of profound intellectual upheaval. For a century, physics had been a comfortable, orderly home, its foundations laid by the great Isaac Newton. The universe was a magnificent clockwork mechanism, a grand cosmic billiard table where every effect had a clear, predictable cause. If you knew the position and momentum of every particle, you could, in principle, calculate the entire future of the cosmos. It was a universe of comforting certainty, a universe that made sense. But by the turn of the 20th century, cracks began to appear in this elegant, deterministic machine. Experiments were revealing a world at the smallest scales, the subatomic realm, that behaved in ways that were not just strange, but utterly impossible. Light, which we knew to be a wave, was suddenly acting like a particle. Electrons, which we knew to be particles, were inexplicably behaving like waves, interfering with each other as if they were ripples on a pond, even when sent one at a time. The old physics was dying, and the search was on for something new, something radical enough to explain the madness. The epicenter of this revolution was not a grand laboratory filled with gleaming monolithic machines. It was a quiet institute in Copenhagen, presided over by a man who looked more like a gentle, pipe-smoking philosopher than a physicist. His name was Niels Bohr. Bohr was the patriarch, the spiritual guide of this new quantum church. Physicists from across the globe made the pilgrimage to his institute, not just to learn, but to argue, to battle, to wrestle with the universe itself. They would talk and scrawl equations on blackboards for days, their debates spilling out of the lecture halls and into the city parks, arguing with a fervour that bordered on religious. They were a generation of young titans, intellectual gunslingers rewriting the laws of reality on the fly, and among them, the boldest, the most brilliant, and perhaps the most audacious, was a young German named Werner Heisenberg. Heisenberg possessed a breathtaking intellectual courage. He looked at the bizarre behaviour of the electron, its refusal to be pinned down, and proposed something that would shatter the foundations of classical thought. He suggested that we stop trying to visualize the atom as a miniature solar system, with tiny electron planets orbiting a nuclear sun. This picture, he argued, was a relic of our clumsy macroscopic world. It was a comfortable illusion we imposed on a realm that owed our intuition nothing. Instead, he and his colleagues developed a new language, a new mathematics, to describe this ghostly domain. And at its heart were two concepts so counterintuitive, so contrary to every ounce of human experience, that they still trouble us to this day. The first of these was superposition. In our world, an object can only be in one place at one time. A book is either on the table or on the floor. A car is in this lane or that one. This is the bedrock of our existence. But in the quantum world, this simple logic dissolves. An electron, before you look at it, is not in any single location. It exists in a ghostly state of all its possible locations simultaneously. It is a wave of pure potential, a smear of probability, occupying a vast range of positions and possessing a range of momentums all at the same time. Imagine a single guitar string vibrating. It's not just playing one note, it's vibrating with a fundamental tone and a cascade of overtones, all of which exist together, creating the rich, complex sound you hear. The electron in its superposition is like that musical chord of reality. It is a symphony of possibilities, all playing at once. It's a state of profound, beautiful, and deeply unsettling ambiguity. This cloud of potential, this mathematical description of all the things a particle could be, was given a name, the wave function. Formulated with genius by the Austrian physicist Erwin Schrödinger, the very man who would later become the quantum world's greatest critic, the wave function was a monumental achievement. It was a tool of incredible predictive power. You could use its elegant mathematics to calculate the probability of finding the electron at any given point, should you choose to look for it. It could tell you, with stunning accuracy, the likelihood of its energy state, its spin, or its momentum. The mathematics worked. It predicted the results of experiments with a precision unmatched by any theory in the history of science. But it came at a terrible philosophical price. The wave function did not describe what a particle is, it described what it might be. It replaced the solid certainty of Newton's clockwork universe with a haze of statistical chance. Albert Einstein, the old guard of physics, was horrified. He could not accept that the fundamental nature of the universe was governed by randomness, famously declaring, "I, at any rate, am convinced that he does not play dice." But for Bohr and Heisenberg in Copenhagen, this was not a flaw. This was the revelation. The universe, at its most fundamental level, was probabilistic. Certainty was an illusion, a comforting fiction that emerged only at the large scales of our everyday world. This led them to the second, and even more radical idea. If a particle exists as a wave of potential, a superposition of all possibilities, why do we only ever see it in one definite state when we look? When you perform an experiment to find an electron, you don't find a ghostly smear. You find a particle, at this specific point, with this specific spin. What happens to all those other possibilities? Where does the ghost go? Their answer, which became the central pillar of what we now call the Copenhagen interpretation, was as profound as it was controversial. The act of measurement, the simple act of looking at the quantum system, is what forces the universe to make a choice. It is not a passive act of discovery. It is an act of creation. The moment an observation is made, the moment a detector interacts with that shimmering wave of potential, the wave function inexplicably collapses. All of those infinite possibilities, all the places the electron could have been, vanish in an instant. Only one remains, plucked from the ether of probability to become solid reality. The chord of music instantly resolves into a single, pure note. The ghost solidifies into a corpse. Think about what this means. Reality, according to the Copenhagen interpretation, is not a fixed, objective thing sitting out there waiting for us to find it. It is a dynamic, participatory process. The universe, in its unobserved state, is a tapestry of maybes, and we, the observers, by the very act of reaching out to touch it, compel it to become an is. This idea was utterly revolutionary. It shattered the classical distinction between the observer and the observed. In Newtonian physics, you could study a system without disturbing it, at least in theory. You were a spectator watching the cosmic drama unfold. But in the quantum world, you were no longer just in the audience. The moment you bought a ticket and took your seat, you were on the stage, part of the play, your very presence influencing the final act. Heisenberg distilled this intrinsic connection into his famous uncertainty principle. It states that there are certain pairs of properties, like a particle's position and its momentum, that are fundamentally linked. The more precisely you measure one, the less precisely you can possibly know the other. This wasn't a limitation of our instruments, a matter of building better equipment. It was a fundamental, unbreachable law of nature. The universe itself imposes a veil of fuzziness, an inescapable trade-off. You can know where the electron is, but in doing so, you lose all information about where it's going. Or you can know where it's going, its momentum, but you must sacrifice any knowledge of its precise location. You can never have both. The certainty of the old world was gone, replaced by an inherent, unavoidable cosmic uncertainty. For the disciples gathered around Bohr in Copenhagen, this was a triumph. They had created a complete self-consistent theory. It was strange, it was weird, it defied all common sense, but it worked. It explained the results of every experiment thrown at it. Physics, they believed, was not about describing how the world is, because such a question was meaningless. Physics was about describing what we can say about the world, and what we could say was governed by the mathematics of the wave function and its dramatic collapse upon observation. This pragmatic, and to its critics deeply unsatisfying view of the universe became the dominant orthodoxy for decades. If you were a physicist, you learned to shut up and calculate. You used the powerful equations of quantum mechanics to build lasers, transistors, and nuclear reactors without losing sleep over the bizarre philosophical implications. But not everyone was willing to be so quiet. Whispers of dissent grew into loud, passionate arguments. What precisely constituted an observation? What was this magical boundary between the fuzzy quantum world of superposition and our solid, classical world of definite outcomes? Does the wave function collapse when a conscious human looks at a dial? Or does it collapse when the particle simply interacts with an inanimate detector? Does a Geiger counter count as an observer, a camera, a rock? The theory provided no clear answer. It simply drew a line in the sand, a cut, as they called it, between the quantum system being measured and the classical device doing the measuring. But it offered no explanation for why this line should be there, or how a collection of atoms in a measuring device, which should themselves obey the laws of quantum mechanics, could somehow gain the godlike power to collapse the wave function of another particle. For many, this was not physics. It was a philosophical sleight of hand. It felt like invoking magic to solve a problem. And among the most troubled, the most intellectually offended by this new dogma was Erwin Schrödinger. He was one of the architects of this strange new world. His wave equation was its mathematical soul. But he had come to loathe the interpretation that Bohr and Heisenberg had built upon his work. He could not accept a reality that remained in a state of suspended animation, a ghostly limbo waiting for an observer to grant it the gift of existence. He believed in a real world, one that existed with or without us. He saw the Copenhagen interpretations collapse as an absurdity, a nonsensical jump that violated the smooth, continuous evolution described by his own beautiful equation. He was determined to show the world just how ridiculous this idea truly was. He needed a way to amplify the microscopic weirdness of superposition, to drag the ghostly uncertainty of a single, unobserved atom up into our own macroscopic world of flesh and blood, life and death. He was about to devise a thought experiment, a cruel and brilliant paradox that would escape the confines of physics and embed itself permanently into the fabric of human culture. He was about to put a cat in a box. This stark new reality, built on the foundations of quantum mechanics, was celebrated as a monumental triumph, a new gospel of physics preached from Copenhagen by Niels Bohr and his disciples. For most of the brilliant young minds who had helped build it, this was the final word. The universe, at its most fundamental level, was simply a game of chance, a shimmering haze of potential that only snapped into focus under the harsh light of our observation. But for one of its principal architects, the Austrian physicist Erwin Schrödinger, this was not a triumph. It was a descent into madness, a surrender of the very soul of science. He, a Nobel laureate who had penned the master equation that governed the wave-like nature of reality, now found himself in a state of profound intellectual rebellion against his own creation. The Copenhagen interpretation, which we have seen place the conscious observer at the centre of reality's creation, felt to Schrödinger like a betrayal. It was philosophical sleight of hand, a declaration of victory by simply refusing to ask the hard questions. Physics, in his mind, was supposed to be about describing an objective world, a universe that existed with or without us, governed by elegant, unambiguous laws. This new quantum orthodoxy, however, suggested a ghostly, provisional world that waited for our permission to become real. In his private letters, his frustration simmered, then boiled over. He felt he was witnessing the rise of a new mysticism, a retreat from reason. He saw colleagues embracing concepts that, in any other context, would be dismissed as nonsensical. He wrote to Arnold Sommerfeld lamenting this and new quantum mechanics that seemed so very ugly. He felt the ground of certainty, the bedrock upon which all of classical physics had been built for 300 years, crumbling into a swamp of probabilities. His chief intellectual sparring partner was Niels Bohr, a man he respected immensely but whose philosophical conclusions he could not abide. Their debates were the stuff of legend, clashes between two titans of 20th century thought. Bohr, the enigmatic Dane, argued that the fuzzy, superimposed state of a quantum particle was its complete description. There was nothing more to say about it until it was measured. Schrödinger, the refined Viennese classicist, found this utterly unacceptable. Surely the particle had a definite position even when we weren't looking. Surely our ignorance did not define its reality. To him, the wave function he had so elegantly derived was a description of our knowledge about the system, not the system itself. But Bohr and his brilliant protégé, Werner Heisenberg, were relentless. They insisted that it was meaningless, even unscientific, to speak of properties that could not be measured. The cat, so to speak, was either in the box or it wasn't. You couldn't ask where it really was before you looked. Schrödinger saw this not as a profound insight, but as an intellectual cop-out. He needed a weapon, not a mathematical formula, not another dense academic paper, but something more potent. He needed an image, a story so vivid, so viscerally absurd that it would force his colleagues to confront the monstrous implications of their own theory. He needed to drag the quantum ghost out of the unseen atomic realm and place it squarely in our familiar macroscopic world. He sought to build a bridge from their abstract equations to the undeniable reality of life and death. And so, in a 1935 paper titled The Present Situation in Quantum Mechanics, he prepared to construct his intellectual trap, a piece of macabre theatre designed not to be performed, but to be contemplated in horrified silence. He was about to build a box, and inside it, he would stage a philosophical execution. Let us follow him now, not into a laboratory of glass and steel, but into the laboratory of the mind, the only place where such a diabolical contraption could ever be assembled. First, he requires a vessel, a fortress of absolute isolation. Imagine a steel chamber, sealed so perfectly that no information, no stray light, no curious vibration can possibly leak in or out. This box is the crucial boundary. It is the dividing line he intends to blur, the wall between the strange, ghostly world of the quantum and our own world of solid, definite things. Inside this silent, dark space, the rules of Copenhagen are supposed to hold sway, unimpeded by the clumsy interference of an outside observer. Everything that happens within is, for now, a closed book. Next, Schrödinger places at the heart of his machine the engine of pure quantum chance. He selects a single radioactive atom, a speck of matter so infinitesimally small, its very existence governed by the probabilistic laws we've come to accept. We know from our previous explorations that this atom exists in a state of superposition. It has not yet decayed, and yet it has decayed. It is a perfect blend of both possibilities, described by a single, elegant wave function. The laws of quantum mechanics give us the precise odds. Let's say there is a perfect 50-50 chance that this atom will decay in the span of 1 hour. The key, for Schrödinger's argument, is that until that hour is up and a measurement is made, the atom is not one or the other. It is, according to Bohr's doctrine, metaphysically both. It is a ticking time bomb of pure potential, but a single atom's decay is a silent, invisible affair. To escalate his argument, Schrödinger needs to amplify this subatomic uncertainty. He needs a detector, a link in the causal chain. So next to the atom, he places a Geiger counter. This is a familiar piece of laboratory equipment, a device designed for one purpose: to register the passage of ionizing radiation. When our radioactive atom eventually does decay, it will emit a particle. This particle will fly into the Geiger counter, which will then produce a distinct measurable signal. A click. The Geiger counter is his intermediary. It is the first step in dragging the quantum event kicking and screaming into the macroscopic world. It is the translator, converting the ghostly language of quantum probability into the brute mechanical language of a physical device. The click of a Geiger counter, however, is still a relatively benign event. It lacks the dramatic finality Schrödinger needs to make his point truly land. He must escalate the consequences further, making them impossible to ignore. His thought experiment now requires a mechanism of execution. Attached to the Geiger counter, he imagines a relay switch connected to a hammer, a simple, brutal, classical machine. When the Geiger counter clicks, it trips the relay. The relay, in turn, releases the hammer, which is held precariously poised, suspended by a thread of logic. With the atom's decay, the thread is cut. The hammer swings. This is the amplifier of doom, a purely Newtonian instrument of cause and effect, set in motion by a fundamentally non-Newtonian trigger. The uncertainty of the atom is now mechanically coupled to the certainty of a falling weight. And what is the purpose of this falling hammer? It is here that Schrödinger introduces the final, horrifying element of his design, the component that elevates this thought experiment from a clever puzzle to an enduring, chilling parable. The hammer is positioned directly above a small, fragile vial, and inside that vial is a lethal poison. Hydrocyanic acid, a substance whose effect is swift and absolute. When the hammer falls, it will shatter the glass. The poison will be released as a vapour into the sealed chamber. The chain of events is now complete. The quantum superposition of the atom, the state of decayed and not decayed, is now inextricably linked through a series of mechanical connections to the state of the vial, broken and not broken. The poison is released and not released. The very air inside the box is now simultaneously lethal and benign. Finally, with the entire infernal apparatus in place, Schrödinger introduces his victim. And he chooses his subject with deliberate philosophical precision. Not a gear, not a dial, not an inanimate lump of matter whose state might be debatable. He places inside the box a creature of flesh and blood, a complex macroscopic system whose state of existence admits no ambiguity. He places inside a cat, a living, breathing being. Why a cat? Because a cat is so unquantifiably, undeniably classical. We understand what it means for a cat to be alive. It purrs, it breathes, it has a beating heart. We understand what it means for it to be dead. It is still, it is cold, there is no in-between. By placing a cat in the box, Schrödinger is issuing a direct challenge. He is forcing his colleagues to apply their strange quantum rules to something they understand viscerally, something for which the hazy language of superposition seems not just inadequate, but grotesque. Now the lid of the steel chamber is sealed. The clock begins to tick. 1 hour must pass. Inside the box, the quantum drama unfolds, shielded from our view. The single radioactive atom, abiding by the laws Schrödinger himself helped to write, enters its 50-50 state of superposition. It is both intact and decayed, and because the entire apparatus is a single, interconnected system, this quantum uncertainty begins to cascade outwards, like a contagion of illogic. Since the atom's state is indeterminate, the Geiger counter, too, must be in a superposition of having clicked and not clicked. This, in turn, forces the hammer into a ghostly state of having fallen and not fallen. The vial of poison is therefore simultaneously shattered and intact. The very atmosphere of the box is a probabilistic blur of safe and deadly. And what of the cat? This is the heart of Schrödinger's attack, the point of his macabre spear. If we are to take the Copenhagen interpretation at its word, if we are to believe that the wave function provides a complete description of the system, then we are forced into a conclusion that defies all reason and experience. The cat, its fate inextricably entangled with that of the atom, must also be in a superposition of states. It cannot be described as simply alive or dead, because the quantum event that decides its fate has not yet been resolved into a single reality. The cat, sealed in its metal tomb, is suspended in an unholy union of existence and non-existence. It is, according to the mathematics, a smear of probabilities. The cat is simultaneously a living creature and a corpse. This is it. This is the moment of reductio ad absurdum, the absurd conclusion to which the accepted logic leads. Schrödinger did not believe for a single second that a real cat could be in such a state. He was not proposing a new physical phenomenon, he was screaming, "Look! Look at the ridiculous, nonsensical place your theory takes us when we follow it to its logical end!" He was using the cat to hold up a mirror to the quantum physicists and show them the absurdity he saw reflected in their ideas. He found the notion of a half-alive, half-dead cat quite ridiculous. For him, this was not a paradox to be savoured, but a clear and damning indictment. It was proof positive that something was desperately wrong, that the theory was fundamentally incomplete. He was directly attacking the so-called measurement problem, the gaping hole at the centre of the Copenhagen interpretation. The theory claimed that superposition persists until a measurement or an observation is made, at which point the wave function magically collapses into a single definite state. But what precisely constitutes a measurement? Is the Geiger counter an observer? If so, why doesn't it collapse the wave function of the atom? Is the hammer an observer? Does the universe wait for a conscious human being to open the box and peer inside? If so, what was the universe doing for the 13 billion years before we arrived to observe it? Schrödinger's thought experiment was designed to show that there is no clear line, no logical place to say, here the quantum world ends, and here the classical world begins. His cat was trapped on that blurry, undefined border, a martyr sacrificed on the altar of a flawed and incomplete theory. The entire diabolical setup was a polemic, a passionate argument disguised as a physics problem. He was telling his colleagues that you cannot confine this quantum weirdness to the atomic realm. It inevitably bleeds out, infecting the world of our experience with its paradoxes. If their theory was correct, then the world of cats and poisons must be just as probabilistic and observer-dependent as the world of electrons and photons. This, for Schrödinger, was an impossible price to pay. He believed in a single, objective reality, one that did not wait for a physicist to open a box to decide whether a cat had lived or died. The fate of the cat, he insisted, was sealed the moment the atom did or did not decay, whether anyone was watching or not. He had laid the trap perfectly. The image was too powerful to ignore, too disturbing to forget. He had created a zombie cat, a ghost in the machine of physics that would haunt the very foundations of quantum theory for the next century. He intended it as a demonstration of failure, a clear sign that the current path was leading physics away from objective reality and into a fog of subjective idealism. But what Schrödinger could never have anticipated was how his brilliant critique, his intellectual protest, would be misunderstood, twisted, and ultimately adopted by the very theory he sought to dismantle. His terrifying vision of an indeterminate reality was about to escape the confines of his thought experiment and take on a life of its own, becoming not a symbol of absurdity, but the most famous and most misinterpreted emblem of the quantum world itself. The cat was out of the box, and so we leave the cat suspended in that ghostly state, a quantum spectre hanging between being and non-being. It's a powerful, chilling image, one that has haunted the edges of physics for nearly a century. You have likely pictured it yourself, that silent, steel-walled prison where life and death are not opposites, but two sides of the same coin, spun by the universe and waiting to land. This is the story we're always told, the ultimate symbol of quantum weirdness. But now, we must ask the most important question, the one that changes everything. What if the story we've all been told is a profound misunderstanding? What if the architect of this famous paradox, Erwin Schrödinger himself, never intended for you to believe in a zombie cat at all? The truth is, this thought experiment was not a window into the quantum world. It was a weapon. It was a philosophical grenade, meticulously crafted and rolled into the heart of the physics community in 1935. Its target was not to explain quantum mechanics, but to expose what Schrödinger saw as a deep and perhaps unforgivable absurdity at its core. To understand how this elegant piece of intellectual protest became the very poster child for the idea it was meant to ridicule, we must go back. We must journey into the mind of a man who helped build this new science, only to become one of its most eloquent and troubled critics. Erwin Schrödinger was not a mystic drawn to the bizarre. He was, by temperament and training, a classicist. He believed in a universe governed by smooth, continuous, and predictable laws, described by the beautiful wave mechanics he himself had pioneered. He saw reality as a flowing river, not a stuttering, pixelated screen that leaped from one state to another only when someone was looking. Yet, the dominant theory of his day, the Copenhagen interpretation championed by Niels Bohr and Werner Heisenberg, proposed just that. It suggested that, at the most fundamental level, reality was inherently fuzzy and probabilistic. An atom, they argued, doesn't possess a definite state until it is measured. Until that moment of intervention, it exists in a blur of all possible outcomes, a superposition of states. For Schrödinger and for his close friend and intellectual ally Albert Einstein, this was a philosophical betrayal. They found the idea of an observer mysteriously conjuring reality into existence profoundly disturbing. What, they demanded to know, constituted a measurement? Does a physicist with a PhD have to be in the room? Could a lab assistant do it? What about a Geiger counter, a machine designed precisely to observe radioactive decay? Does its click count as the definitive moment of observation? Or does the machine, being made of atoms itself, also enter a state of superposition, a state of both having clicked and not clicked, until a conscious mind registers its result? The Copenhagen school offered no clear answers, only a vague, undefined boundary, a conceptual wall separating the strange, probabilistic quantum world from our familiar, solid classical world. They called this the Heisenberg cut, but for Schrödinger, it was less a scientific principle and more an act of intellectual surrender. It was a line drawn in the sand to stop people from asking uncomfortable questions. He saw this ambiguity not as a feature of the universe, but as a failure of the theory. In his letters to Einstein, you can feel his mounting frustration. He felt his colleagues were abandoning the core pursuit of physics to describe an objective reality that exists independently of our awareness of it. He believed they were replacing causality and clarity with a kind of fashionable mysticism, a spooky philosophy disguised as science. So he decided to force the issue. He would take their premise, that superposition is real, and that it persists until a measurement is made, and he would follow it to its most logical, most grotesque conclusion. He would design a device, a diabolical machine, to amplify the microscopic uncertainty of a single atom until it infected the macroscopic world, our world. He would build an intellectual Trojan horse, and inside he would place a cat. The choice of a cat was a stroke of rhetorical genius. It was not an abstract pointer on a dial or a nameless particle. It was a warm, living, breathing creature. Something we have a deep intuitive connection to. You cannot be ambivalent about the state of a cat. It is either purring or it is tragically still. By linking the fate of this familiar animal directly to the quantum spin of a single, invisible atom, Schrödinger was forging an unbreakable chain of logic. He was saying to Bohr and Heisenberg, "You tell me this atom is in a superposition of decayed and not decayed. Fine. But I have built a machine where that microscopic superposition is the trigger for a macroscopic event. My mechanism is flawless. A hammer, a vial of cyanide, a life. Therefore, he argued, if your premise is correct, you're not just committed to a fuzzy atom, you're committed to a fuzzy cat. You must accept a reality where this creature is, in your own words, smeared out, in a combination of alive and dead." This was not a proposal, it was an accusation. It was a challenge thrown down with the full force of his intellect. The entire purpose of the experiment was its absurdity. He was holding up a mirror to the Copenhagen interpretation and showing it a monstrous reflection, hoping his colleagues would recoil in horror and say, "No, of course not. That can't be right. Our theory must be incomplete." He expected them to see the paradox not as a feature of reality, but as a fatal flaw in their understanding. He was using the classic philosophical argument of reductio ad absurdum, proving a proposition false by showing that it leads to a ridiculous consequence. Schrödinger wasn't describing quantum mechanics, he was mocking a particular interpretation of it. He was laying a trap, and the bizarre, unthinkable nature of the alive and dead cat was the bait. He believed no sane physicist could seriously entertain such a possibility. But here, history takes a deeply ironic turn. The trap he laid was so captivating, so unforgettable, that future generations would forget it was a trap at all. They would instead fall in love with the bait. The story of the cat escaped the confines of dense academic papers and philosophical debates among Europe's top physicists. It had all the elements of a gripping myth, a hidden mystery, a life-or-death gamble, and a conclusion that seemed to defy common sense. It was simply too good a story to remain shackled to its original critical context. Over the decades, as quantum mechanics became part of our cultural lexicon, the thought experiment underwent a strange transformation. Pop science writers, eager to convey the strangeness of the quantum realm, seized upon the cat. It was the perfect metaphor, stripped of all its original philosophical baggage. The crucial detail, that it was intended as a critique, was often trimmed away, treated as a footnote, or ignored entirely. It was far more exciting to present it as a literal mind-bending truth about the universe. The thought experiment became a spectacle. It was no longer a question aimed at a flawed theory, but an answer about a bizarre reality. It was presented as proof that the quantum world was a place of pure magic, where our looking could kill or save an animal inside a box. Even within the physics community, the story began to shift. As a new generation of physicists came of age, taught from textbooks that presented the Copenhagen interpretation as established fact, Schrödinger's cat was often framed differently. It was taught not as an unresolved problem, but as a classic paradox that students had to learn to accept. It became a rite of passage, a test of one's ability to abandon classical intuition and embrace the weirdness. The original intent, to highlight the ambiguity of measurement, was subtly reframed. The cat became an illustration of superposition, rather than a protest against its illogical extension into our world. The profound challenge Schrödinger had posed was domesticated, turned into a quirky but manageable feature of the quantum landscape, and so the great misinterpretation was cemented. The public came to believe that physicists thought a cat could actually be simultaneously alive and dead. Science fiction authors ran with the idea, creating tales of quantum ghosts and observers who shape reality. The symbol had completely devoured the substance. What was lost was not just a historical detail, it was the very soul of Schrödinger's argument. His true question was never, is the cat alive or dead? His true question was, where does the madness stop? At what point on the chain, from the decaying atom to the Geiger counter to the hammer to the vial to the cat, and finally to the human observer, does the universe decide to make up its mind? Where is the seam in the fabric of reality that separates the shimmering, uncertain quantum world from the solid, definite classical one? This is the real puzzle of Schrödinger's cat. The Copenhagen interpretation simply drew a line and refused to explain its existence. Bohr essentially argued that the measuring device itself is classical, and that the interaction between the quantum system and this classical device is what forces a resolution. But this begs the question, why is the measuring device classical? It too is made of atoms, which must obey quantum laws. So where does the quantumness go? How does a collection of fuzzy, probabilistic atoms band together to become a solid, definite object that can perform a measurement? This is the measurement problem in its starkest form, and Schrödinger's cat is its most powerful, most visceral illustration. It's a problem that the founders of quantum mechanics never truly solved. They simply built a philosophical framework that allowed them to perform calculations and make predictions despite it. And those predictions were astonishingly successful. Quantum mechanics works. It gives us lasers, transistors, nuclear power, and the entire digital world you're experiencing right now. Its mathematical precision is unparalleled in the history of science. For many working physicists, that is enough. The shut up and calculate approach became a pragmatic way forward. The philosophical headaches, the questions about the nature of reality, could be left to the philosophers. But for Schrödinger, this was never enough. He, like Einstein, believed that the goal of science was not just to predict outcomes, but to understand reality. A theory that could not describe what was happening in the universe when we weren't looking was, in his view, an incomplete one. He didn't want a theory of knowledge, he wanted a theory of being. The tragic irony is that his brilliant attempt to expose this incompleteness backfired spectacularly. His perfectly articulated argument against a blurry reality was transformed into the ultimate symbol of a blurry reality. The warning label he placed on the theory was mistaken for a promotional poster, and in popularizing the paradox, we defanged it. We turned a deep and troubling philosophical crisis at the heart of modern physics into a quirky piece of trivia, a fun fact about a zombie cat. We learned to stop worrying and love the superposition. But the ghost of that cat still haunts the halls of physics, because the question it was designed to ask has never been answered. That invisible line between the quantum and the classical, the Heisenberg cut, remains as mysterious and undefined today as it was in 1935. It is a line that you cross every moment of your existence. You are a macroscopic being, made of an astronomical number of quantum particles. You are a walking, talking, thinking solution to the measurement problem. Yet the science that so perfectly describes your constituent parts cannot fully explain how they conspire to become you, a single, definite, classical entity, never in a superposition of being in two places at once. We have not resolved the paradox Schrödinger raised. We have simply learned to live with it. We have papered over the conceptual chasm he revealed, but the chasm is still there. If we dare to peer over the edge, we find that the foundations of our reality are not nearly as solid as they seem. And this forces us to a precipice. If the most successful theory in history contains such a profound, unresolved paradox at its centre, what does that mean for our understanding of the cosmos? If Schrödinger was right, and the Copenhagen interpretation's vague notion of measurement is an insufficient answer, then we are left with a universe in crisis. We are left with a choice. Either the theory itself is incomplete, a mere shadow of a deeper, more comprehensive reality yet to be discovered, or reality is far, far stranger than even a half-dead, half-alive cat could possibly suggest. It is this choice, this branching path forged by Schrödinger's brilliant act of rebellion, that would lead physicists to imagine new universes, to split reality itself into infinite copies, all in a desperate and beautiful attempt to finally let the cat out of the box. And so the paradox, once unleashed, refused to return to its cage. Schrödinger's diabolical invention was never meant to be a serious proposal for a real-world experiment. It was an act of intellectual rebellion, a beautifully sharp weapon designed to pierce the heart of the prevailing quantum orthodoxy. He had taken the strange, ghostly rules of the atomic world and dragged them kicking and screaming into our familiar solid reality. In doing so, he exposed a wound in the foundations of physics, a question so profound and so stubbornly unanswered that it became known simply as the measurement problem. For the pioneers of quantum mechanics, the founding fathers like Bohr and Heisenberg, the answer was pragmatic if unsatisfying. An observation, they argued, a measurement, is what forces the universe to make a choice. The act of looking, of interacting with a quantum system, is what shatters the delicate superposition, what collapses the wave of potential outcomes into a single concrete reality. Before you open the box, the atom is both decayed and not decayed. The cat, therefore, is both alive and dead. The moment you look, the universe commits. But this elegant sidestep concealed a chasm. What, precisely, is a measurement? Is it the click of a Geiger counter? The swing of a hammer? Or does it require something more? Something conscious? The theory remained unnervingly silent on this point, a vagueness that felt less like scientific rigour and more like a philosophical get-out clause. Does a physicist's gaze hold a special collapse-inducing power that a cat's does not? What about a simple camera, set to record the outcome? Does the wave function collapse when the film is exposed, or only when a human later develops and looks at the picture? The questions multiplied, each more absurd than the last, peeling back the layers of our assumptions about reality itself. The Copenhagen interpretation, for all its predictive power, had drawn a mystical line in the sand between the quantum world and the classical world, the world of probabilities and the world of facts. And Schrödinger's cat was now pacing right on that line, a phantom sentinel guarding an arbitrary border. This was the true crisis. The very act of observation, the supposed bedrock of all science, had become the central mystery. It was as if a detective could solve any crime, but had no idea what a clue was. For a time, some of the most brilliant minds on the planet were forced to entertain ideas that bordered on the supernatural. Perhaps it was consciousness itself, the spark of human awareness, that served as the universe's ultimate arbiter. This notion, championed by figures like the legendary mathematician John von Neumann and later physicist Eugene Wigner, proposed that the entire chain of events, the atom decaying, the counter clicking, the hammer falling, the poison releasing, the cat dying, remains in a colossal, ever-expanding state of superposition until the information finally reaches a conscious mind. In this view, the entire physical world, even a creature as complex as a cat, could exist in this ghostly quantum fog until a human observer enters the scene, their awareness acting like a divine switch that throws the universe into a definite state. You, the observer, would not be discovering the cat's fate. You would be deciding it retroactively at the moment of perception. It's an idea that is both deeply egotistical and profoundly unsettling, placing humanity at the very centre of cosmic reality. It suggests that without a conscious witness, the universe remains a smear of undecided possibilities. But it's also scientifically untestable, a philosophical dead end that pushes the problem one step further back without truly solving it. If a human mind collapses the wave function, what about a chimpanzee's, a dog's, an ant's? Where do we draw the line of consciousness capable of birthing reality? The search for a more physical, less mystical answer was on. The problem wasn't the mathematics. The Schrödinger equation worked perfectly to describe the evolution of the wave function, the spreading sea of possibilities. The problem was the violent, instantaneous rupture of that evolution, the collapse. It was an add-on, a rule imposed from the outside without any mechanism to explain it. Physicists needed to find the saboteur, the hidden agent responsible for demolishing quantum superpositions in the world we see every day. For decades, the mystery deepened. It seemed as though the universe was playing a trick, enforcing one set of rules for the impossibly small and another for everything else, with no clear jurisdiction in between. But the clue, it turned out, was not hidden in the consciousness of the observer, but in the one thing that had been systematically ignored in the thought experiment: the environment itself. The box was not a perfect, hermetically sealed vessel, isolated from the rest of the universe, and that, it turns out, makes all the difference. This is the gateway to a concept of breathtaking power and subtlety, an idea that has reshaped our entire understanding of the quantum to classical transition. It is called quantum decoherence, and it suggests that the cat is never, not even for an instant, truly alone in the box. It doesn't need you, the human observer, to collapse its wave function, because it is being relentlessly and continuously observed by trillions upon trillions of other particles every single nanosecond. Think of a quantum superposition not as a binary state, but as a fragile, intricate pattern, a delicate vibration of possibility. It is like a single, pure musical note ringing in a perfectly silent, insulated concert hall. Within that perfect isolation, the note can sustain its purity indefinitely. But what happens if you open the doors of the concert hall to the chaos of a bustling city? The pure note is instantly overwhelmed, drowned out by a cacophony of car horns, distant sirens, and the murmur of the crowd. Its coherent singular identity is lost, smeared into the background noise. It hasn't vanished, but its special, isolated state has been destroyed. It has decohered. This is precisely what happens to a quantum system when it touches the outside world. Every object in our universe is constantly interacting with its surroundings. It is bombarded by photons of light, jostled by vibrating air molecules, and bathed in its own thermal radiation. Each one of these interactions, no matter how small, carries away a tiny, fleeting whisper of information about the object's state. Consider our unfortunate cat. Let's imagine, for a moment, that the impossible happens and the cat is placed into a superposition of alive and dead. The alive part of the cat has a certain temperature, a certain position. It is breathing. Its warm body radiates infrared photons into the box, billions of them, every second. The air molecules in the box, countless septillions of them, rebound off its living, breathing fur. Now consider the dead part of the cat. It is cold still. It radiates far fewer infrared photons. The air molecules bounce off it with a different energy. Each of these interactions creates a record. A single photon bouncing off the living cat now carries the information the cat is here and it is warm. A nearby air molecule, having failed to be moved by the cat's breath, now carries the information the cat is still. What happens is a form of runaway entanglement. In earlier sections, we saw how two particles can become entangled, their fates linked no matter the distance. But this was a gross oversimplification. Entanglement isn't a private affair. The universe is the ultimate gossip. That photon, having bounced off the living part of the superposition, is now entangled with it. That air molecule, having jostled the dead part, is now entangled with that. But it doesn't stop there. The photon flies off, hits the wall of the box, and a particle in the wall is now entangled with the photon, which is entangled with the cat. The air molecule bumps into another air molecule, and the entanglement spreads like a contagion. Within a fraction of a picosecond, an impossibly short sliver of time, the information about the cat's state, alive or dead, has leaked out and become entangled with the entire environment of the box. The initial clean superposition of alive cat plus dead cat has morphed into a monstrously complex entangled mess of alive cat entangled with alive cat environment, plus dead cat entangled with dead cat environment. The original, pristine coherence between the alive and dead states has been irrevocably shattered. The two possibilities can no longer interfere with each other because they are now shackled to two completely different, mutually exclusive environments. Think of it like trying to reconstruct a single, coherent image from two photographs that have been shredded and mixed with the shredded pieces of a million other, completely different photographs. The information is, in theory, still there, but it is so widely distributed and hopelessly scrambled that it is for all practical purposes lost forever. To see the quantum weirdness, to witness the interference pattern that proves superposition, you would need to gather every single particle that interacted with the cat, every photon, every air molecule, every atom in the walls of the box, and measure them all in a coordinated way. You would have to perfectly reverse the chaotic journey of every single piece of information that leaked out. You would have to effectively track down and read the entire universe. It is a task of such gargantuan cosmic impossibility that it will never happen. Decoherence, then, is the universe's own continuous, inescapable measurement process. It is the universe acting as its own observer. It doesn't need a conscious human. The environment itself is the most diligent and invasive observer imaginable, constantly probing and recording, destroying quantum purity wherever it finds it. This explains why we never see macroscopic objects in superposition. A bowling ball is not in a superposition of here and the moon because the photons from the sun, the cosmic microwave background, and even stray interstellar dust particles are constantly measuring its position, pinning it to one definite location. A teacup on your desk isn't a ghostly cloud of potential teacups. It's a solid, classical object because the air in your room is performing trillions of location checks on it every femtosecond, destroying any quantum fuzziness before it could even begin to form. The quantum world is not protected by a magical barrier. It is simply protected by isolation. The only reason we can see quantum effects in carefully controlled laboratory experiments is because scientists go to extraordinary lengths to create that isolation, shielding single atoms or photons from the relentless chatter of the outside world. They create a tiny temporary echo of that silent concert hall. So, let's return for one last time to the box. The radioactive atom is placed in its superposition. For a brief, impossibly fleeting moment, it exists as a wave of potential. But the instant it interacts with the Geiger counter, decoherence begins its work. The information about the atom's state, decayed or not decayed, entangles with the electrons in the counter. That entanglement cascades to the mechanism of the hammer, which in turn becomes entangled with the vial of poison, whose shattering or non-shattering state becomes entangled with the air, which becomes entangled with the cat. By the time you, the human, even begin to walk towards the box, the choice has already been made and brutally enforced by the universe itself. The superposition of the cat was never a stable, long-lived state. It was a theoretical ghost, an ephemeral possibility that was annihilated by the relentless scrutiny of its own environment in a time so short it makes the blink of an eye seem like an eternity. You are not the observer who collapses the wave function. You are merely the latecomer, the archaeologist arriving long after the event, uncovering a classical fact that was already written into the fabric of reality by the inescapable process of decoherence. It seems like a perfect solution, a clean, physical mechanism that explains why our world looks solid and dependable, while the quantum realm remains a swirling mist of possibility. It demystifies the measurement process, removing the conscious observer from their privileged and troubling position at the center of reality. Decoherence explains why the quantum rules which govern everything give rise to the classical rules we experience. It bridges the gap, and yet, a deep and profound mystery remains, a ghost that decoherence, for all its power, cannot exorcise. Decoherence tells us how. The superposition is effectively destroyed. It explains why we can no longer see the interference between the alive cat and dead cat possibilities. It forces the system into a set of classical-looking distinct options. But it does not tell us why we, in our experiment, perceive one of those options and not the other. The mathematics of decoherence still describe a universe that contains both a live cat entangled with its live cat environment and a dead cat entangled with its dead cat environment. All the possibilities in a way still exist. They are just separated from each other, unable to interact. So why, when you open the box, do you only see one of them? Why does your reality proceed down the path of the living cat, while the reality of the dead cat seems to vanish? Decoherence has brilliantly explained the process of choosing from the menu of reality, but it has failed to explain who or what places the final order. Has the other possibility simply evaporated into nothingness? Or could it be that it hasn't vanished at all? Could it be that in the moment of that final, irreversible measurement, reality itself forked into two? One universe for the scientist who finds a living cat, and another running parallel for the grieving scientist who finds a dead one. The measurement problem, it seems, has not been solved. It has merely been transformed into an even grander, more mind-bending question. The cat was one thing, but what had happened to the universe? For decades, the question hung in the air, a philosophical ghost haunting the halls of physics. Where does the quantum world, with its spectral uncertainties and ghostly superpositions, give way to our solid, dependable reality? At what point does an atom, existing in a haze of probability, become the chair you're sitting on, an object with one definite location? For Erwin Schrödinger, the line was obvious. A cat simply could not be both alive and dead. The absurdity of his paradox was meant to be a warning, a line in the sand. But what if the universe never saw that line? What if Schrödinger's absurdity is in fact the deepest truth of our existence? Today we are no longer just thinking about the box. We are building it, piece by agonizing piece, in laboratories across the globe. We are pushing that shimmering, uncertain boundary, not with philosophy, but with lasers, vacuum chambers, and objects of truly startling size. The thought experiment has become a physical quest, a high-stakes expedition into the very nature of what it means to be real. This is the story of how we began to put the cat, or its modern-day equivalents, into the box for real, and how the results are forcing us to confront a universe far stranger than even its discoverers could have imagined. Our journey begins not with a cat, but with the simplest and purest carriers of quantum information, particles of light, photons. In laboratories shielded from the slightest tremor or stray electromagnetic whisper, scientists have perfected the art of creating what Einstein so famously called spooky action at a distance. They craft pairs of photons that are profoundly, inextricably linked, entangled cosmic twins born from the same quantum event. Measuring a property of one, like its polarization, instantly influences the property of its partner, no matter how vast the distance separating them. But the true power of this technique for our purposes lies in using one of these photons as a trigger, a quantum executioner for a microscopic version of Schrödinger's device. Imagine a setup where one entangled photon is sent on its way, its fate undetermined. The other is directed towards a detector. If this second photon is detected, a signal is sent, perhaps flipping the polarization of another beam of light. If it is not detected, because its path was uncertain, existing in a superposition, then nothing happens. Until we measure that first, distant photon, the trigger photon exists in a superposition of having been detected and not detected. Consequently, the beam of light it controls is also in a superposition, both flipped and not flipped simultaneously. This is our first, most elemental cat. It is not flesh and blood, but a delicate state of light, yet it holds the same paradoxical duality. It is a system held in suspended animation, its fate tied to the quantum roll of the dice of its entangled twin. When we finally measure that distant photon, the spell is broken. The wave function for the entire system collapses in an instant. We discover the fate of the trigger, and in doing so, we seal the fate of our light cat, forcing it into one definite reality. These experiments, repeated millions of times with unfailing accuracy, proved that the core mechanism of the paradox was not a flaw in the theory. It was a fundamental feature of the universe. The weirdness was real. But photons are ethereal, massless. To truly challenge Schrödinger's argument, we had to take the next audacious step. We had to try this with matter. We had to build a bigger cat. This brings us to a laboratory in Vienna, a place that has become a world capital for quantum exploration. Here, researchers decided to scale up the experiment dramatically. Their choice of subject. Not an atom, but a complex molecule, a buckyball, composed of 60 carbon atoms arranged in a beautiful spherical cage like a microscopic soccer ball. This is an object with weight, with structure, with thousands of constituent protons, neutrons and electrons, an object teetering on the edge of the world we consider classical. The challenge is monumental. The larger an object is, the more ways it can interact with its environment. A single stray atom of air, a forgotten photon of heat, even the subtle gravitational pull of a scientist walking past the lab bench, any of these can act as an observation. Any interaction, no matter how slight, is enough to measure the molecule's position, forcing it out of its delicate quantum state and destroying the superposition. This phenomenon, known as decoherence, is the constant enemy, the universe's own relentless attempt to enforce classical rules. It's the reason you've never seen a chair in two places at once. The universe is constantly looking at it. To create a molecular Schrödinger's cat, the scientist had to build the most isolated place on Earth. Inside a vacuum chamber, pumped down to pressures lower than deep space, they fired a beam of these buckyballs. They cooled them to near absolute zero to quell their internal vibrations. They then sent them towards a barrier containing incredibly narrow slits, a modern version of the famous double-slit experiment that first revealed the wave-like nature of particles. If the molecule behaved like a classical object, a tiny soccer ball, it would pass through one slit or the other, creating two distinct bands on the detector screen behind it. But that is not what happened. Against all classical intuition, these complex molecules, these tangible pieces of matter, did the impossible. They began to create an interference pattern, the unmistakable signature of a wave that has passed through both slits at the same time. Each individual molecule, an object comprised of 60 atoms, had been in a state of superposition. It had travelled two separate paths simultaneously. It was, for a fleeting moment, a real, physical object in two places at once. Pause for a moment and let the sheer, breathtaking strangeness of that sink in. This wasn't just a mathematical abstraction, it was a physical reality. Scientists had coaxed a piece of the macroscopic world into behaving like a quantum phantom. Since those pioneering experiments, the bar has been raised again and again. Researchers have now placed molecules made of up to 2,000 atoms into superposition. They have even done this with biological molecules, the very building blocks of life itself. We are no longer just on the border of the classical world. We are making deep incursions, dragging larger and larger chunks of reality back across the quantum divide with us. We are demonstrating that there is no obvious preordained size limit where quantum mechanics simply switches off. The line Schrödinger thought was so clear is proving to be a phantom, receding further and further away the harder we look for it. The weirdness doesn't just stay in the subatomic basement. It seems to permeate everything, a hidden layer of reality lurking just beneath the surface of our perceptions, waiting for the right conditions to reveal its ghostly nature. But even a molecule of 2,000 atoms is still invisibly small. To truly confront the paradox, to build something genuinely cat-like, we would need to go bigger still. We would need to build a machine that was itself a quantum object, and that is precisely what is happening now, at the absolute cutting edge of experimental physics. We are entering the realm of quantum acoustics and mechanics, where scientists are attempting the unthinkable, placing a human-made object, an object large enough to be seen with the naked eye, into a state of superposition. Imagine a tiny sliver of aluminum, about the width of a human hair, engineered to vibrate like a microscopic tuning fork. In our everyday world, this tiny paddle, this cantilever, can either be vibrating or still. There is no in-between. But in the quantum realm, there is. The goal of these experiments is to cool this mechanical object down to its quantum ground state, a temperature so unfathomably cold, mere millionths of a degree above absolute zero, that all classical thermal vibration ceases. It becomes perfectly still, a quiet canvas upon which to paint a quantum masterpiece. Using exquisitely precise microwave pulses, scientists can then nudge this tiny paddle with a single quantum of energy, a single photon. This single photon, however, is first placed in a superposition of both being there and not being there. Because the photon and the paddle are now a coupled quantum system, the paddle inherits the photon's uncertainty. The result is a sliver of metal that is simultaneously vibrating and not vibrating. It is a mechanical Schrödinger's cat, a tiny drumhead caught in a paradoxical state of being both struck and silent. To achieve this, the isolation required is almost beyond comprehension. The experiment must be shielded from seismic rumbles, from acoustic noise, from the blackbody radiation of the chamber walls, from the faint hum of its own electronics. The entire apparatus becomes a gravitational gyroscope, a fortress against the universe's constant prying. The act of measurement itself becomes a profound challenge. How do you check if the paddle is in a superposition without looking at it, and thereby destroying the very state you wish to observe? The solutions are ingenious, involving further entanglement with other quantum circuits that can probe the system without collapsing it, reading the ghost of its state from a safe distance. In one landmark experiment, a team managed to entangle two of these mechanical oscillators, two distinct spatially separated drums, each about the size of a red blood cell. They were linked by a superconducting cable, and for a moment they shared a single unified quantum state. A vibration in one was intrinsically linked to a vibration in the other, a form of mechanical, spooky action. These are not abstract particles anymore. These are solid objects, each containing trillions of atoms, behaving as a single quantum entity. We have built Schrödinger's box, and we have placed inside it not a living thing, but a piece of our own technology, a tiny vibrating ghost in the machine. We have proven, beyond any reasonable doubt, that the principle of superposition is not some strange quirk confined to the world of the very small. It is a universal law that applies just as well to a vibrating mirror as it does to an electron. The classical world we perceive is not fundamental. It is an emergent property, a consequence of constant, unavoidable observation by the environment. We don't see quantum effects in our daily lives simply because we, and everything around us, are bathed in a sea of decoherence. These experiments do more than just vindicate the strange predictions of quantum theory. They force us to ask the deepest questions of all. Schrödinger invented his cat to highlight a perceived flaw in the Copenhagen interpretation, the idea that observation or measurement is what collapses the wave function and creates a definite reality. His paradox was a challenge. What constitutes a measurement? Does it require a conscious observer, a human mind? Or is any physical interaction enough? The modern experiments with vibrating mirrors and macroscopic molecules provide a stunningly clear answer to part of that question. A single stray photon of heat is enough. A collision with a single molecule of air is enough. The universe itself is the ultimate observer, its constant chaotic interactions relentlessly measuring every large object, pinning it down to a single classical state. Consciousness, it seems, has nothing to do with it. The process is entirely physical, yet this profound revelation only deepens the central mystery. We now see that the transition from quantum to classical is not a hard line, but a gradient, a process of decoherence. We can fight it in the lab, creating temporary pockets of quantum reality for larger and larger objects, but this raises an even more unsettling possibility. If there is no fundamental size limit, does this mean that, in principle, a large object, a chair, a planet, a cat, could exist in a superposition if it were perfectly, absolutely isolated from the entire universe? The theory says yes, the experiments are trending in that direction. We have found Schrödinger's cat not as a single creature, but as a universal principle woven into the fabric of space-time. The absurdity he pointed to was not a flaw in the mathematics, it was a glimpse into the raw, uncollapsed nature of reality itself. We live in the collapsed world, the world of definite outcomes, the world after the measurement has been made. But these incredible new tools are allowing us to peer behind the curtain, to glimpse the ghostly realm of pure potential from which our solid world continuously emerges. We have scaled the mountain of theory and now stand on the precipice, looking down into the quantum heart of existence. We have confirmed that the box can be built, that the superposition is real. But this triumph has only led us to the final, most terrifying question of all, the one that Schrödinger's paradox was always truly about. We understand the mechanics inside the box, but what is the ultimate nature of the force that insists on opening it? Undefined. And so, after navigating the baffling corridors of quantum probability, after witnessing the universe split into infinite copies of itself, and after grappling with the very meaning of measurement, we arrive back where our journey began. not with a cat, but with a man, Erwin Schrödinger. A titan of physics, a Nobel laureate who helped write the fundamental equation of this new strange reality, yet found himself profoundly disturbed by the philosophical abyss it had opened. The thought experiment was his protest, a reductio ad absurdum designed to expose what he saw as the sheer lunacy of applying quantum rules to the world we know, the world of solid objects and definite outcomes. He intended to build a bridge of logic from the bizarre realm of the atom to our familiar classical world, and then to show us all that the bridge was impassable, that the logic must be flawed. He presented his macabre little parable, this fusion of household pet and radioactive decay, not as a genuine reflection of nature, but as a stark warning. Look, he was screaming into the intellectual winds of his time. This is the ridiculous, nonsensical world your Copenhagen interpretation demands. A world where life and death are held in abeyance, smeared out in a haze of potential until a conscious mind intervenes. He meant for the cat to be a casualty of flawed reasoning, a martyr for common sense. But history and physics had other plans. In one of the most sublime ironies in all of science, his perfect instrument of critique was so brilliantly conceived, so viscerally unsettling, that it escaped his control. It became the ultimate emblem not of the theory's failure, but of its astonishing paradigm-shattering success. The ghost he summoned to haunt his colleagues refused to be exorcised. Instead, it took up permanent residence at the very heart of the quantum mystery, becoming the eternal mascot for the profound weirdness he had hoped to dispel. The paradox was never truly about the welfare of a hypothetical feline. It was, and remains, a philosophical scalpel forged to dissect the very tissue of reality. Its true purpose is to force our hand, to make us confront the intractable questions that lurk in the seam between the quantum and the classical. What precisely constitutes an observation? Is it the click of a Geiger counter, a machine registering a datum? Is it the moment light from a screen hits a human retina? Or does it require the full, mysterious engine of consciousness to collapse the wave function and force the universe to make a choice? The cat in the box is a stand-in for this monumental ambiguity. It embodies the schism in our understanding, a line drawn in the cosmic sand that we still do not know how to cross. For nearly a century, this single, elegant puzzle has served as the ultimate intellectual stress test for every proposed model of existence. Think of it as a gravitational center around which all interpretations of quantum mechanics are forced to orbit. The Copenhagen interpretation, which we have seen, simply severs the connection, erecting a wall between the two realms and leaving the cat's fate ambiguous until the moment of measurement, a solution that Schrödinger and Einstein found deeply unsatisfying, an abdication of explanatory duty. Then you have the many worlds hypothesis, a breathtakingly bold proposal that solves the paradox by embracing it completely. In this view, the box is never open to reveal a single outcome. Instead, the entire universe cleaves in two. In one branch, a grief-stricken physicist finds a tragically deceased cat. In another, parallel universe, a relieved colleague finds the creature alive, well, and presumably quite annoyed. The superposition is never broken. It is simply distributed across the burgeoning canopy of an infinitely branching reality. Here, the cat is a genesis point, a constant ongoing act of cosmic creation, where every quantum choice spawns new timelines, new histories, new versions of you and I. Other, less grandiose but equally profound ideas continue to vie for supremacy, each using the cat as its proving ground. Pilot wave theories, like those championed by de Broglie and Bohm, suggest the particle was never in two states at once. They argue that its position was always definite, merely guided by an invisible, unseen quantum wave, meaning our ignorance was the source of the uncertainty, not a fundamental feature of reality itself. In this picture, the cat's fate was sealed the moment the experiment was conceived. We just didn't have access to the hidden information needed to predict it. And then there are objective collapse theories, which propose that superposition is a fragile state that naturally and spontaneously breaks down on its own when a system reaches a certain threshold of mass or complexity. In this scenario, the cat, or perhaps even the Geiger counter itself, is large enough to be its own observer, collapsing its own wave function without any need for a conscious onlooker. The universe, it seems, can look at itself. Each of these frameworks, each of these desperate, brilliant attempts to map the true territory of the real, must first pass through the crucible of Schrödinger's box. Each must provide a coherent, satisfying answer to that one tormenting question. What happens inside, in the dark, when no one is looking? The fact that we still ask this question, that the brightest minds on the planet still argue passionately about the answer, reveals the thought experiment's enduring power. It is an intellectual irritant, a beautiful and persistent grain of sand in the oyster of physics that continues to produce pearls of profound insight. It taught us that our classical intuition, honed over millennia of surviving on the Serengeti and building civilizations, is a woefully inadequate tool for navigating the fundamental workings of the cosmos. It revealed that at the deepest level, reality is not a collection of miniature billiard balls behaving in predictable ways. It is a shimmering, probabilistic tapestry of potential, a sea of information where concepts like here and there, or even is and is not, become blurry and intertwined. The cat is our ambassador to that world, a reluctant traveller who brings back tidings that we are still struggling to fully comprehend. Its dual state of being is a mirror reflecting the dual state of our own knowledge, a profound understanding of the mathematical rules, coexisting with a deep and unsettling ignorance of the underlying reality those rules describe. But the legacy of Schrödinger's cat is no longer confined to the chalkboard debates of philosophers and theoretical physicists. The ghost has gotten into the machine. The very principles that seemed so absurd, so paradoxical when applied to a living creature, have become the foundational resources of a technological revolution. We have moved from being haunted by the strangeness to actively harnessing it. The field of quantum computing is, in its essence, the engineering of Schrödinger's cats on a massive, intricate scale. A classical computer bit is a simple switch, a definite 0 or a 1. It is classical, reliable, and unambiguous. But a quantum bit, a qubit, is something else entirely. It is a controlled microscopic system, an electron's spin, a photon's polarization, that is deliberately placed into a state of superposition. It is, simultaneously, both 0 and 1. It is the cat, alive and dead, encoded in the language of information. By linking these qubits together through another ghostly quantum phenomenon, entanglement, the spooky action at a distance that so troubled Einstein, we can create a computational system of unimaginable power. A quantum computer doesn't calculate one possibility at a time, it calculates every possibility at once. It explores that entire branching, many worlds-like reality of potential solutions simultaneously in a vast parallel process. The alive and dead state of the cat, once a symbol of absurdity, is now the very source of its power. The central challenge for quantum engineers today is a direct echo of the original paradox. How do you protect this fragile, potent superposition from the act of observation? The slightest interaction with the outside environment, a stray magnetic field, a tiny vibration, a flicker of heat, can act as a measurement, collapsing the superposition and destroying the calculation. This phenomenon, known as decoherence, is the quantum engineer's mortal enemy. They spend their careers building the most perfect, isolated boxes imaginable, using cryogenic temperatures and vacuum chambers to shield their qubits from the universe, allowing the cat to remain in its ghostly state just long enough to perform its magic. This technological progeny extends far beyond computing. Quantum cryptography promises truly unhackable communication, using the principles of observation to secure information. If an eavesdropper tries to intercept a key encoded in quantum states, the very act of their measurement inevitably disturbs those states, leaving behind an unmistakable trace. The paradox itself becomes the ultimate security guard. Quantum sensors are now being developed that can measure gravitational fields with such exquisite precision they could map hidden structures beneath the Earth's crust, or detect the faint neurological signals of the human brain in unprecedented detail. They achieve this by leveraging the extreme sensitivity of systems held in superposition, systems that are, for all intents and purposes, cousins of our cat, reacting to the faintest whispers from their environment. We are, in a very real sense, learning to use the universe's fundamental weirdness as a tool. The intellectual puzzle box Schrödinger designed in 1935 has become a blueprint for the 21st century's most transformative technologies, a journey from a philosophical headache to the engine of a new industrial age. And yet, for all this astonishing progress, for all our newfound ability to manipulate the quantum world to our own ends, the core mystery remains. We have learned how to keep the cat in its state of suspended animation. We have learned how to put its dual nature to work. But we still do not fundamentally agree on what that state is. The measurement problem, the question of how and why the shimmering world of quantum potential gives way to the single, solid reality we experience, is as unsolved today as it was in Schrödinger's time. The cat is not a relic of a bygone era of physics. It is a living question, a wound in our understanding of the world that has stubbornly refused to heal. It represents the frontier, the chalk line drawn on the floor of the laboratory, beyond which our comprehension fails. It reminds us that science is not a completed monolith of facts, but a dynamic, unfolding process of inquiry, forever pushing against the boundaries of the known. It forces us to be humble. It stands as a permanent testament to the fact that the universe is under no obligation to make sense to us, to conform to the logic baked into our primate brains. Reality, at its most fundamental level, may be something far stranger, far more fluid, and far more magnificent than our language can properly express or our intuition can comfortably grasp. The quest to understand the cat in the box is the quest to understand our own place in the cosmos. It is the search for the nature of consciousness, the meaning of information, and the very structure of existence. It is not a problem to be solved and filed away. It is a cosmic koan to be contemplated, a source of endless fascination, and a perpetual spur to the imagination. The frustration that drove Erwin Schrödinger to create his famous paradox has, over the decades, transformed into something else entirely, a deep and abiding sense of awe. In the end, the most powerful lesson of Schrödinger's cat has nothing to do with physics. It is about the nature of a great question. A great question is not one that has a simple answer. A great question is one that spawns 1,000 new questions, that reframes the world, that pushes an entire field of inquiry into new and fertile territory. The cat in the box was never the point. The point was always the box itself, that dark, sealed, mysterious space that represents the absolute limit of our knowledge. And the point was the act of questioning, the irrepressible human need to ask, what's inside? For nearly a century we have been asking. We have built cathedrals of mathematics, fantastic new technologies, and daring new visions of reality in our attempt to answer. And though a final consensus truth may still elude us, the journey itself has utterly transformed our world. The misunderstood, paradoxical cat, born of frustration, remains science's most potent and enduring symbol of our unending, unyielding, and utterly glorious quest to look inside the box and comprehend the deepest mysteries of being.